What is the cheapest way to generate embeddings? And the best way for that matter? Naturally, with OpenAI blowing up lately, many of us are using OpenAI's embedding models to generate embeddings for our projects. And for good reason, their latest model, Text Embedding Ada 2, performs quite well and it's dirt cheap. They are $0.0001 per 1,000 tokens as of June 13th, 2023. So that's very inexpensive, but are they really the best? There must be other models, ideally open source, that exist, right? What if we wanted to self-host the embedding models? Can't do that with OpenAI, really. Or what if we don't want to depend on an external API like OpenAI? Maybe we don't want vendor lock-in. Maybe we need to work completely offline. That's a totally valid use case. Or maybe you're just looking for which embedding model actually performs the best. So yes, they do exist, thankfully. That's what this video is going to be all about. And in case you didn't know, these models have actually existed way before OpenAI made embeddings popular. So today we're going to cover a quick background on embeddings. We're going to talk about a popular set of open source embeddings that you could self-host and even run directly in the browser. We're going to go over how to actually use them, and we're going to find out there's like a whole nother world here when it comes to embeddings that I want to uncover in this video. We'll find out that each embedding model actually has some benefits over other embedding models for different use cases, such as the input size limits, the dimension size outputs, which models are designed for different types of tasks. And that's right, embeddings actually can be used for many different purposes. I think a lot of people today use them for search, but there's things like clustering, classification, re-ranking, retrieval. We're going to talk a little bit about this to understand when you might want to use one model over the other, because as you start to go down the rabbit hole of all these embedding models, it can start to become just a bit overwhelming trying to understand when to use each one, right? We're going to talk about how good these models actually are and how we decide how do we even rank these, especially compared to OpenAI. And finally, we're going to talk about what to expect in the future when it comes to embeddings. There's some really exciting stuff coming up on the horizon, and let's stay ahead of it. Okay, here is a blank TypeScript Node.js project. We're going to be using TypeScript for this video for a couple of reasons. Number one, many of you guys who follow this channel are JavaScript/TypeScript devs and would like to see all this new AI stuff from the TypeScript perspective. Number two, later on in this video, I'm going to be showing you actually how to do the same thing within the browser directly, which is kind of incredible. And of course, that's going to need to be in JavaScript. And number three, I think most everyone knows Python is like the ML AI dominant language. And that's amazing. I love the ecosystem that Python has. But personally, I like to see these concepts and tools brought to other languages like TypeScript. So if you are a Python dev watching this video, what I would say is feel free to still follow along if you're interested in this content, i.e. you're interested in learning more about embeddings. What I'm about to show will absolutely translate to Python. In fact, it's actually probably even easier to do in Python, as you'll find out shortly. All the docs I'll be going through are actually Python by default. So I've already scaffolded this repository, super basic, nothing fancy at all, just your classic tsconfig. Try to keep it as bare bones as possible here. Here's our package.json, just a couple scripts to do some TypeScript compiling. And finally, we have an index.ts file here, which can act as our entry point. By the way, I will upload this code as always to GitHub, so you can check that out in the video description. Feel free to follow along if you like. If you've gotten this far and you don't know what an embedding is, let me give you a quick refresher. Basically, embeddings give you a way to relate content together. For example, for text embeddings, you can have two different paragraphs and figure out how similar those two paragraphs are to each other. And when I say similar, I'm not talking about like keyword similarity, also known as lexical similarity. I'm talking about how similar their true underlying meanings are, right? And this is something you can only really get with a neural network model. To me, the best way to think about embeddings is on a chart. Text with similar meaning will be plotted together on the chart, and those that are dissimilar will be far apart. And the coordinates of these embeddings, so if you were to look at a 2D chart, the X and Y axis, that represents the embedding, those two numbers. Of course, in reality, you need way more than 2 dimensions. Most models will produce in the hundreds or thousands of dimensions. If you want to get a deeper dive on embeddings and how you might use them in a real application, like a custom ChatGPT style search for your knowledge base, feel free to watch my video on how I built Clippy GPT for the Supabase documentation. All right, with that out of the way, let's address another important piece when it comes to embeddings. Embeddings aren't just for text, right? They can exist for many different data types like images or even audio. Just like text embeddings where you can figure out how similar two pieces of text are, image embeddings, as you'd expect, allow you to actually figure out how similar two different images are to each other, right? All you need is a model that can take an image and generate an embedding from it, and you get the same functionality functionality. If you've ever wondered how Google's reverse image search works, where you can actually give it an image itself, so instead of text, you use an image to search it, and it will come up with a bunch of other images that are similar to that image, along with like their descriptions, that's image embeddings. Okay, so now once again, we're building a Node.js app right now. Why Node.js? Well, I think probably for many of you, whether you're already doing this or planning to do something with embeddings, quite likely you're going to be wanting to do this from the back end, right? Lots of times when you're generating embeddings, you're probably going to be storing this in a database somewhere. So a database like Postgres can actually do it with the PG vector extension. As I've talked about before in my other video, you can also use Pinecone, and there's a ton of other specialized vector databases out there. And to connect to these, you're going to be connecting from the backend. So I want to start with that. Again, we will be actually checking out a browser version 2, and you can decide on your own if that's something that you actually want to run in a real application. I can definitely see some use cases there too. So we're in our index.ts just to prove that this is working. Let's do a quick console log. And hello world, I think, is overrated. Let's do a modern hello world, which is just going to be emoji based. Do a little bit of a wave. We'll do an npm run dev, and there we go. There is our wave. Perfect. So where do we start here when it comes to embeddings? So there's two main places we're going to hang out today. The first is SBERT.net, which if you search for pretty much anything to do with these open source embeddings I'm about to go through, SBERT.net comes up because they're kind of one of the main sources of truth around this idea of sentence transformers or sentence embeddings. This site was originally created by Niels Reimers and Irina Gurevich. These guys wrote the original paper on sentence BERT, which is kind of where this all started. Basically, as we'll find out more throughout this video, one of the first sentence embeddings was proposed in this paper using the BERT language model, and sentence BERT or SBERT is a modification on that BERT network model to actually output a single embedding that represents an entire sentence that can be used for exactly what we all use embeddings for, similarity. And we'll dive more into that as we go. Now, you might notice right off the bat here that this website is talking about how sentence transformers is a Python framework. And so you might be saying, Greg, what the heck? You told me we're working in TypeScript. Yeah, we are. Don't worry. Like I said, all of the industry right now uses Python for these things. And so again, if you are using Python, feel free to just follow this as is. Essentially, they provide this sentence transformers framework for Python that makes it super simple to load in these different models and actually generate embeddings on them. Now, we're going to be doing something similar, very similar, except we're going to be using TypeScript. Okay, and the second site we need to be familiar with is Hugging Face. I'm going to go about this assuming that Hugging Face is somewhat new to you, just to kind of cover all our bases here. So first off, what is Hugging Face? Essentially, this is a company who took the Hugging Face emoji and made a company around it. No, but seriously, these guys, you can kind of think of as the hub for machine learning models and data sets and tooling, right? So in the same way you might use GitHub to store your source code, quite likely you would consider using Hugging Face to actually store your machine learning models and the data sets that contributed to training those models. They have this thing called Spaces, which is kind of like a demo playground environment you can create that basically connects to these models and allows you to test them right there in the browser. And that's kind of their three main offerings here. So let's go to models. So models is literally a list of neural network models that you can use for various purposes, right? As you can see here right now, we're filtering by tasks. And so these are showing some of the different types of tasks you might need a model for, right? So some of these might stand out to you. Text to image, right? This is very popular these days. I'm sure you've heard of Stable Diffusion or some of the companies, Midjourney. These guys are using text to image models where you give it a prompt and it's going to try to produce an image, right? You can go the other way around. You got an image and you want it to describe that image. What is this image actually all about? What's contained in it? So that's image to text and so on. Lots of really cool things in the computer vision space where you can give it an image and it's actually going to try to predict the physical depth within that image. Can be very useful. We're not going to have time to go through all of these, but definitely check them out. It's quite amazing what's possible these days and quite inspiring too. So why do we care about Hugging Face today in this video? Well, as you might guess, we're going to be pulling in our models from Hugging Face in order to run them. And we're actually going to talk about a couple different ways we do that. If you're wondering, okay, are we actually downloading these models to disk and then running them there? Are we going to be running them on a server somewhere? Great questions. We're going to be covering that. Okay, so back to SBERT. I think it's worth pointing out that even though this site is called SBERT, since that original paper, there's been a ton of new embedding models that have surfaced, which are mentioned right on this website. My guess is the original authors created this site and then just kept on expanding off of that with these new models. And honestly, nowadays, I don't think we're actually going to even be using the actual SBERT model, but this site's going to contain just a ton of really useful information on sentence transformers in general. Okay, so I'm sure you're dying to see what these models are and how to use them. So let's jump into pre-trained models. And this page is going to go over these different models that we're able to use and which ones are best for different purposes, right? As you can see, they're hosting these on Hugging Face, which is essentially the de facto place, again, that everyone's hosting their models. If we come down here, first we have this all dash models. These are basically categorized for different purposes. As you can see here, the all models are for general purpose. So if you don't need anything specialized and you want to use these embeddings for multiple purposes, which we're going to get into, you might choose an all-based model. And you can see here they've actually done some benchmarks on these, the performance, so how well each of these actually performed on their task, and then how fast they were, also how big the model is. And all these factors are quite important. I mean, especially for the purposes of this video, quite likely you guys are wanting to actually deploy these things, use them in a real application, right? We want to get beyond the theory and turn this into something real, right? So immediately we have to be considering things like how fast these models are and how much disk space they're going to take up when we're deciding which one to use. And they have a little bit of commentary here. You can see that the all MPNet based V2 model has the best quality according to their benchmarks, while the all mini LM L6 V2 is 5 times faster and still offers pretty good quality. And of course, as you can see here, much faster and also quite a bit smaller, say about 5 times smaller. And you'll find out shortly, this all mini LM is actually very popular. We see this a lot right now, and it's for pretty good reason. If we keep scrolling down, we're now getting into models that are specialized for certain tasks. And we're going to have a better discussion on what these tasks are in a second, but just bear with me here. There's a specific task called semantic search, which is given a query, how well is that able to match with a document? And at the surface level, this might just seem like, how is this special? Isn't this just what all embeddings do? And actually, no, this is specific to search, right? This is also known as a retrieval type task where you're trying to match queries, which are actually typically very small, right? How big is London? You know, they might be less than 20 characters, and we want to match those with potentially very long documents or sections within a document. And that's actually not a default behavior, right? You would need to train the model very specifically to understand and, perform well at matching these small queries with these long documents. Otherwise, by default, it might actually only match pieces of text that have a similar length, which is known as semantic textual similarity, or you might see it as STS. And you'll see that the way they're able to make these models more specialized is, of course, by training it on different data sets, right? They're focusing on very specific data sets to support this task. So in this case, you see these multi-question answer models for the semantic search are trained on 250 million question answer pairs from various sources, including Stack Exchange, Yahoo Answers, Google Bing search queries, and more, right? And as you'd expect, all these sources would mostly have this nice query response, short, long pairing, right? So that's one set here. There's another one, MS Marco. This has 500,000 real actual queries in the Bing search. So again, also targeting that search use case. And we have a set here based on the BERT architecture, and then down here using the mini LM as we saw before, but this one is focused just on search versus before the one we were looking at was the all. Now, another thing to mention real quick as you're going through these is different models will produce embeddings of different formats, right? So in the case of these models here, you can see that you need to be using dot product with these, right? And if you're familiar with the different ways to calculate similarity, you'll know that there is such thing as dot product, cosine similarity, and Euclidean distance, right? And these are 3 different ways to actually calculate that similarity. Any kind of vector database will support these operations, but not all models will support all of them, right? Essentially, in order to support all of them, the output of the models needs to be normalized, which means it's a unit vector, has a length of 1. I'm not going to go deep into linear algebra theory right now, but just kind of be aware of this aspect when it comes to the output vectors. Moving down, we have also multilingual based models, which targets another task called bitext mining. Bitext mining describes the process of finding translated sentence pairs, right? So maybe you haven't thought about this one, but another perfect use case for embeddings, right? If I have a sentence in English and then another sentence in Portuguese, and they supposedly mean the same thing, perhaps that's valuable to me, depending on whatever application I'm building, to understand that similarity and know when two sentences from two different languages are similar, right? So there are certain models that are trained for that exact purpose because they're trained on a data set that actually pairs two different languages. So there's models specialized for that as well. Okay, and finally, we have image and text models, which is also known as multimodal models. And I'm going to talk more about this later near the end of the video, but these ones are super, super cool. Essentially what's happening is, if you remember me talking about earlier how embeddings don't just apply to text, right? They could apply to images, how similar two images to each other. But if we have a multimodal model, we actually can take an image or a piece of text and generate an embedding within the same vector space. And what that means is I could take a piece of text, generate an embedding. I could have an image and also generate an embedding. And if I compare those two embeddings, I'm actually comparing how similar that text is to that image, which is actually pretty incredible that this is possible. This opens up like tons of possibilities for things like image captioning. Here they call zero-shot image classification. What does that mean? Whenever you see zero-shot, this is talking about the ability to classify, in this case, an image without the model having ever seen it before. Traditionally, right? If I want my model to be fed an image and it be able to classify that. So if I want it to give it a hamburger and it knows that's a hamburger, and I give it a piece of pizza and it knows that's a piece of pizza, I would have needed to train the model with those specific classifiers, right? I would have to have a pizza, hamburger, etc., and train it with real pictures of that, right? Zero shot means we never actually came up with those labels specifically during the training. It's more of a general use case here, but it's still able to classify that, right? And that's thanks to these image and text models. So at this point, you might be thinking, okay, I'm somewhat overwhelmed right now because you just showed me kind of this wall of models. You've explained the different purposes, but I don't know right now which one I should use. And say I go with one of these all models because they're general purpose. How am I really going to be able to pick them? I mean, you said that the all mini LM is good, so maybe I'll just go with that. Okay, now's a good time, I think, to show you this same information, but from a different perspective. If we head on back over to Hugging Face, they have done a lot of really good work in the embedding space with a project called MTEB, or Massive Text Embedding Benchmark. And as they talk about in their blog post here, MTEB is a massive benchmark for measuring the performance of text embedding models on diverse embedding tasks. So literally the entire purpose of this project, which they have written a paper on, is to evaluate embedding models. And this is amazing for people like you and me who aren't necessarily interested in going through each of these one by one, trying to understand what their purpose is supposed to be and measuring their performance against some standardized data set. Hugging Face has already done this for us. This is amazing. And of course, the most interesting part of this is their leaderboard. So let's open up their leaderboard. And if you don't remember anything else from this video, probably the MTEB leaderboard is maybe the one thing you should remember. This is a really great reference for different embedding models. And also, I believe they're continuing to update this, right? So over time, as inevitably new models are going to come out, they're going to be scoring them and placing them on this leaderboard. And you might notice right off the bat here, we actually have OpenAI's text embedding 802 right in here. So this leaderboard isn't just those open source models I was showing you earlier. This leaderboard actually has kind of all the models that the public is aware of, including closed source ones like OpenAI's text embedding 802. And this is super handy, right? Because now we can actually see, wow, we actually have 5 models that potentially have better performance than OpenAI. So some things to notice with this table is we are tracking the embedding dimensions, right? Dimensions is the output size of our vector. So those of you who have experience with OpenAI, this might look familiar, right? Text embedding 802 has 1,536 dimensions. And you'll actually notice compared to some of these other ones, that's a little bit more on the high side. We're actually getting more around 1024, 768, and even down to 384 for some of these smaller ones. Okay, next thing to notice is sequence length. Sequence length is talking about input tokens, right? So again, coming at it from the OpenAI perspective, just because I think so many of you guys have that background here. If you've been able to wrap your head around this idea of tokens, which is basically, they're not a one-to-one to a character, but they're also not a one-to-one to a word. What is a token? It's like usually a part of a word. So if you had a sentence and you were to feed that into any of these models, well, these models have no understanding of symbols and characters on their own. Rather, they have an understanding of tokens. And so probably one of the best ways to visualize this is OpenAI's tokenizer, right? So if you were to type in a piece of text, I like ham sandwiches, can never spell sandwiches right. You can see here that OpenAI's tokenizer has broken down the words into these tokens, which funny enough is actually basically one token per word. So it kind of sounds like I'm lying right now. I'll show you another example, but if we look at the token IDs that map to each of these, right? So that I maps to 40, like maps to 588, and so on. These token IDs are what these embedding models can actually understand, right? We need to tokenize them. So the point I was trying to make is you're not always going to get that one-to-one mapping, which I got wrong here. Sometimes you'll have, what's like a less common word? I like grilled cheese and bacon. Oh, I'm on struggle cert right now. Okay, where is Waldo? Okay, close enough. So as you can see here, Waldo is actually broken into two tokens. How did it decide to do that? Well, there are different tokenizers out there. Essentially, the idea behind a lot of these tokenizers is you want to take the most commonly seen character sequences and generate a single token for that, because in the world of language, that word comes up quite often, or that sequence of characters rather comes up quite often. So according to this, Waldo itself isn't seen as often as just walled combined with something else, right? So the algorithm used here decided that that should be broken there. And like you can see, if I add two question marks, it's actually considering these two question marks as one token. So instead of having, what did that used to be for one question mark? It was a 30. So instead of having two 30s in a row, when I add another question mark, it's actually a whole new token for two question marks, right? So this kind of proves that tokens have nothing to do with specific characters. It's all about a sequence of characters and how often they're seen, right? OpenAI's model must have seen double question marks quite a bit. I mean, if it was trained on the internet, I would expect that. Let's add 3. Yep, that's another token. 4, another token. 5, yet another token. 6. Okay, now as soon as I get to 6, it's now broken up into a 4 and a 2. There's a very specific algorithm behind the scenes that does this. Without going too far down the rabbit hole, I always say this, followed by going down the rabbit hole. The algorithm used for OpenAI is called byte pair encoding, which you might have seen abbreviated as BPE or diagram coding. And essentially it uses a lookup table to do that mapping. This video is not going to be about byte pair encoding, but there are lots of great videos actually that describe this. So feel free to look that up and check those out. Now, it's worth noting that BPE is not the only type of tokenizer. We have another one here called word piece tokenization. And word piece, essentially different models use different tokenizers, right? As you see here, word piece was actually the tokenizing algorithm created by Google for the BERT, original BERT model. And it's used for BERT and a bunch of variants and MPNet. So back to SBERT, all MPNet base v2 or the mini version, these would use that word piece tokenizer. As you can see here, it's very similar to BPE in terms of how it was trained, but the actual tokenization is done differently. If you're interested to learn about exactly what those differences are and how that algorithm works, definitely check out Hugging Face's guide here on word piece tokenization. But for our purposes, that is the gist of what I wanted to cover here. So back to leaderboard, again, those tokenizers matter when it comes to the input sequence length. And one thing you might notice here is all these models are around 512, except for text embedding 82 by OpenAI, and they have this massive 8,191. And at first that might seem like, well, what the heck, everyone else must be so far behind. But in reality, I think in many embedding generation use cases, there's a good chance you're going to want to keep your input sequence relatively low anyways. I've talked about this before in another video, but say you have a massive document, say an article or a blog post or a piece of documentation or a PDF document, and you want to generate embeddings on it in order to do some search later on. It's not necessarily the best practice to try to generate embeddings on that entire document as a whole. Like in the case of this model, you might actually be able to accomplish that. Usually it would be better practice to try to split that document into smaller pieces before generating embeddings. And the reason for that is, well, a couple things. Number one, if there was subsections within that document that matched, now you can actually link the user directly to that subsection rather than just the page as a whole. Depending on your use case, maybe you don't care about the whole document. Maybe you only care about actually extracting parts of that document for your use case. Like if you're building like a ChatGPT style bot and you want to provide it context, typically it's better to actually have subsections instead. And then number three, I'm not sure there's a lot of data on whether these massive input models like text embedding 82 can actually represent all of that information in a single embedding accurately. I think there's a bit of debate on, even though this model can take in a massive input size, is it really creating a meaningful representation of that document when you get past, say, 512 tokens anyways, right? So I would say don't let that number there stop you from considering models other than text embedding 82. Okay, and moving on, what are the rest of these columns talking about? Well, this is talking about those different tasks, right? So we've already talked about some of them. We've talked about search, which is what Hugging Face is calling retrieval. We've talked about semantic textual similarity, which is STS, but we also have some other ones here. So we got clustering. When would clustering be useful? Well, what about related information, right? If you're writing a blog post and at the bottom you want to have other posts related to this one and you want those to be generated automatically, you could generate embeddings on the post title or maybe a bit of the content or a summary of the content and use those embeddings to find other posts that have similar content. Again, I find the best way to think about this is on a chart, right? If they have a bunch of embeddings plotted in a cluster together, they probably have similar meaning and you could pull from any of the other ones close by as related content. There's another one here, summarization. So this is a model that intentionally tries to match a long document with a summary of that document and how similar those are. So this would be a use case where if you for some reason had both a document and a summary of that and you want to know if they were related, this is the metric they use to score that type scenario. So I'm not going to go into details on every little one. I will show you how to find more details on these because if you're like me, it bothered me that I couldn't figure that out. Up here at the top, they actually break them down, right? By text mining, this is the language-based ones. Retrieval, STS, these are all the same things. I don't believe these are actually ranked in these tabs, so don't get confused that all mini L6 is number 4. Like I don't think that's true here. But I couldn't find anywhere here that actually explained like what do each of these really mean, right? Thankfully, if you go back to their blog post, they have the original paper that they wrote on this, the massive text embedding benchmark. And if we open that guy up and scroll down, we can see that they have a nice sections on the task and the evaluation. So they go through each one: by text mining, classification, clustering, pair classification, re-ranking, retrieval, STS, summarization. So there you go. If you're interested to actually learn what each of these really mean, then come here and check those out. Actually, I would recommend it because say that you're most interested in retrieval because you're building search, right? What you might do is you might rank this now by those that scored best for retrieval specifically. Come back over here, and unfortunately this rank doesn't change. This is still based on the original one, so you're just gonna manually count it. But now you can see, okay, well, interestingly now 1, 2, 3, 4, 5, 6. Interestingly, text embedding 82 is still 6. But maybe you had your eye on this E5 small v2, which only has 384 dimensions, and we're going to talk about this in a second, but that's actually a good thing in my opinion. This is now 7th, whereas if we go back and sort by the average of all of these, which is what they consider their all-time rank, this E5 small v2 is actually 8th here, right? So definitely worth understanding exactly what your use case is, coming in here, sorting by that use case, and evaluating which model you want to use based on that. Okay, Greg, you've talked a lot, but can we go ahead and build something already? I mean, this is what you guys signed up for when you are watching a video from this channel. But yes, let's build something. Okay, I mentioned earlier there is potentially 2 different ways we can generate embeddings. One way is using an API, which means we're going to connect to some server somewhere that will actually perform the actual embedding generation, and then it's going to return the result back to us. Or number two, we can actually run the model locally on our own machines and generate it that way. So let's start with the first API-based approach. And naturally, Hugging Face, being the hub of all these models, is the one providing these APIs. So in the documentation, we're going to come down to the Hugging Face.js docs, where they've actually built a JavaScript library that we can just use directly that will essentially connect to their hosted API, run a very specific model with whatever inputs we want, along with parameters for them, and then return a response. And this approach is going to feel very similar to OpenAI's approach because it's essentially the same thing, just more generic, right? OpenAI is, of course, limited to the models that they support. So GPT 3, 3.5, 4, embeddings, also DALL-E, which is their image generation service, like Stable Diffusion. Whereas Hugging Face, essentially you can run, well, any model that they support as an operation, right? So they've wrapped all the common tasks. If you guys remember the tasks we were looking at earlier under models, tasks, each of these has a function. So things like translation between languages, text to image. Just using this, you can actually use Stable Diffusion to generate an image from a prompt, which is pretty awesome. Now, real quick, in case you're not using JavaScript or TypeScript, they do have documentation on the inference endpoints themselves. So again, this is just a regular web API. So using whatever language you want, essentially, you can just check out their Swagger API docs, and they list out all their different endpoints for all the different inference logic. But we're going to come back to huggingface.js. Now, note here real quick, they have two libraries here. They have one called Hub, which is actually talking about connecting to this hub itself. So think of it more like a management API if you're trying to like manage your models and data sets. That's not what we're interested in right now. We're interested in their Inference API, which we can install through that package. You can even use these with Dino, and from there we can just go ahead and call these functions. They make it very simple. Now, just like OpenAI, you're going to need to pass in a access token, right? Since this is an API hosted by Hugging Face, naturally they're going to need to rate limit this. Now, it is actually free. Let's go look at the pricing real quick. Okay, so actually from their Inference-API page, if you scroll down here, they do mention that the use of the Inference API shared infrastructure is free. So as of now, I think you're going to be able to hit this API for free, especially like for development purposes. You'll have no problem. However, as soon as you want to use this in a real prod application, you're definitely going to need to be using a dedicated instance, right? Because right now you're just using shared infrastructure, which has no guarantees. You're going to want to be on dedicated infrastructure, which if we come here, their new page is all about that. So essentially you're selecting your model, choosing your cloud provider, and they'll basically manage the instance for you, hosting your model, which is quite convenient. I mean, traditionally you'd have to do all of that yourself, right? So this is a huge win. Of course, remember, we're talking about their Inference API. We're going to also talk about another approach where we can run this ourselves. So stay tuned for that. Okay, let's start by installing the Hugging Face Inference API. And we're actually going to install one more dependency here called .env. Likely, if you're a JavaScript developer, you have heard of .env. .env will essentially allow us just to save our Hugging Face token into an environment variable file and then load that in to the code, because we never want to hard code our API keys directly into our code. That is bad practice. Okay, installation is complete. Let's go ahead and do that now. Let's go new file, call it literally .env, and actually let's do .env.local. This just indicates it's a local environment file, because in reality, if you were to build an app that would run on production, you'd have a different set of API keys for that. So let's follow best practices here. We're going to create an environment variable called Hugging Face token. And here's where we're going to paste that Hugging Face token. To get that, you'll need to just sign up for an account. Once you sign in, you'll see your profile picture here. Click on that. You can go down to settings, and then you'll see a tab for access tokens. Click on that, and then go ahead and click new token. By the way, if it asks you for a role for your token, go ahead and just select read. This is just gonna be a read-only token. Once you have that, you'll come here and just paste that directly after the equal sign. And then real quick here, I'm gonna add our .env to our getignore, just because we don't want to be committing those files. Okay, now from our index, let's go ahead and import the inference package. So let's go ahead and copy these two lines of code. The inference package exports a HF inference class, which we'll create a new instance of. This is where access token will go. So with Node, this will be process.env. and then we call that our Hugging Face token. Of course, you can call this whatever you like. Now, which of these tasks corresponds to embeddings? Is there a function called generate embeddings? And the answer is no, actually. There's a different name for it. Hugging Face calls this feature extraction. And if we come back to our models here, you can see that's actually the first one here. It's under the multimodal category, which is appropriate. Basically, it means feature extraction can be used for different types of media, right? In our case, we're focusing on text right now. So for us, let's go ahead and come back to our MTEB leaderboard, and let's choose one of these models to generate embeddings for. Now, one of these that stands out to me is the E5 small v2. You might remember me mentioning that the 384 dimensions being small is a good thing. Why is that? Well, if you're generating embeddings, you're almost always generating them because you're looking to perform some sort of similarity search. And to do that search, you're either going to use dot product, or sometimes called inner product, cosine distance, or Euclidean distance. And you could run these algorithms either in whatever language you're using. So say we're using TypeScript, we could generate them there, which we will actually do today just because it's easy. But alternatively, especially in production, most likely you are running these calculations in a database, and ideally a database that supports vector operations. So if you followed my other video on this, you'll know there's a extension for Postgres called pgvector. Let's take another quick look at that. So quick recap, pgvector is an extension you can install onto a regular Postgres database, and suddenly you now get access to this brand new data type called vector. The size of the vector represents the number of dimensions, and it's just another column in your database, another data type for our columns, right? So you would create a column for your embedding, store all your embeddings in that column, and then now you can perform a similarity search using one of the three operators it supports: Euclidean distance, inner product, or cosine distance. Now, if you've already gone down this rabbit hole, then you may or may not be facing limitations with performance, right? I mean, once you store enough information, it might not be practical to perform the similarity search without an index, right? Because without an index, it's a sequential scan, meaning you're literally comparing your embedding to every single row in the database in order to perform that query, right? Whereas with an index, you're not necessarily doing that. Now, when it comes to vector indexes, pgvector implements one such index called an IVF flat index. IVF stands for inverted file index, and this deserves its own video in and of itself. Actually, if you're interested in this specific type of index, I would highly recommend James Briggs. He has a really amazing video describing inverted file indexes and some nice visuals around that. I'd highly recommend watching his video on that. Anyways, reeling myself in, trying not to go too far down this rabbit hole. The point I want to make here is, at scale, you're going to face some challenges with embeddings, right? And indexes aren't necessarily a foolproof solution here, right? First of all, indexes, when it comes to IVF flat indexes, you're actually trading recall for speed, which means as soon as you add the index, you actually will, sometimes minor, but you will get a different query result once you have the index versus without. And that's just because that's part of how the index optimizes it. It's not searching every single other embedding anymore. It's actually scoping that to a smaller group, and that's by design. And on top of that, when you have enough information in your database, creating your index can actually be quite a long operation. It can take potentially a very long time to generate the index in the first place. It can also take up a lot of memory. So you might actually find out that you're, after waiting for a long time, find out that you don't have enough memory on your Postgres instance in order to generate the index. So definitely some challenges you can face here, right? All these challenges, starting with speed of the query, where this all starts from the first place. That's why we're creating the indexes. And even if we do want indexes, the speed and memory footprint of creating the index, these are all proportional to our dimension size, right? Think about it. Forget indexes for a second. If we're just doing a single comparison between two embeddings and we're doing, let's say, dot product between them, dot product is essentially just multiplying each element of one vector with the corresponding element of another vector, right? It's literally that simple. So if we had two vectors, in this case, it'd be like a three-dimensional vector with three values each, 2, 7, 1 for the first, and 8, 2, 8 for the second. Doing the dot product is literally just taking 2 times 8, 7 times 2, and 1 times 8, adding them all together, and then the result being the dot product. So you can imagine the larger these vectors are, So in the case of embeddings, the higher number of dimensions will result in more multiplication operations that need to happen, right? Hopefully that's pretty straightforward. So if you think about it from that perspective, picking a model with less dimensions should actually be super desirable, right? Without an index, these are going to be much quicker to calculate. And then with an index, it's going to use less memory and can potentially generate that index quicker. Now, intuition might say, okay, if there's less dimensions, then it must be like a worse model, right? It must not perform the same as a model with higher dimensions. But as you can see here, like as long as we trust Hugging Face's evaluation here, then a model like E5 small v2 is 8th. And look how many other ones are below this, right? And many of these have a much larger dimension size. Yet, according to these benchmarks, E5 small v2 actually still performs quite well, right? So I would not be using the dimension size as the way you're evaluating performance at all. I would be using a proper benchmark like this. Okay, so enough on that rabbit hole. I've talked up E5 small v2 enough. Let's go ahead and use that guy. But just before that, I'd like to take a moment to quickly thank the sponsor of this video, Brilliant. Brilliant.org is a website that teaches you computer science and math. And I thought this sponsorship is actually quite relevant for this video based on some of the courses that they offer. For me, the specific course that I was most interested in was their introduction to neural networks. With all the AI stuff blowing up these days, personally, I'm the type of person who really wants to know what's happening under the hood. And I really don't like when there's too much magic happening. So I want to know how it actually works under the hood. And I found that the neural network course actually did a really good job of breaking down neural nets at a very simple level and then kind of expanding on that. I'd say that's one of the number one value adds that Brilliant.org has to offer is just like their nice visuals and simplicity. Also, I find they wrote the lessons in a way that kind of forces you to read them step by step rather than just like overwhelming you with a bunch of information. And I'd say like neural networks specifically aren't the easiest thing to understand. So the fact that they can make that simple is impressive. Worth noting, they have more lessons than just AI. They have data science, tons of math if you're into that. If you are interested in trying out Brilliant, I do have a URL you can jump to, which is brilliant.org/rabbit hole syndrome. They said that the first 200 people will get 20% off their annual subscription. So if you're interested, jump on that. And if you did miss it, they do offer a full 30 days for free. So again, if it is something you're interested in, feel free to give that a shot as well. I will throw that link in the description. Thanks again, Brilliant. Let's get back to embeddings. Okay, back to our Inference API. So let's go ahead and copy the feature extraction function. We'll paste that here. Now, real quick, keep in mind I'm using a top level await here. Basically, top level awaits, meaning awaits from the root of the file, is only supported when you're using ES modules. So in my package.json here, I have a type module. So just FYI there in case you're getting an error. If you can't use type module, then just wrap this guy in a function. Traditionally, I would call this async function main. Do my awaits inside of here. Right? And then just call main at the end. But we no longer need that in this case. Okay, so model, we're going to use our E5 small v2. Let's go ahead and open that in a new tab. This is what Hugging Face calls the model card. Just information about the model. It's like a README. And you can get the name of it. So it's just like GitHub, right? You got your organization or your user followed by the name of it. Let's go ahead and copy that. Come here, we'll paste that here as the model. And then we can pass in our inputs. And we can test that out by running a npm run dev. Now, notice that this actually is going to take a little while to load. And the reason for that is Hugging Face's Inference API is using shared infrastructure. So literally under the hood, it has to spin up some sort of container or VM, probably a container, for this model within an environment, under the hood to support generating these embeddings, and then return that to us. So there's such a thing as a cold start versus a warm start. Basically what that means is a cold start is it actually has to spin up that environment on the fly, which is why it can take so long sometimes, but then subsequent times will be more or less immediate, as you can see here, because it's already still running. And I don't know the exact timings they use, but if you wait long enough, then it will spin back down again, unless people are constantly using it. Of course, if you're looking to use their API and you want it to always be warm, then you would be looking into one of their paid offerings. So let's take a look here. Looks like we're getting a bunch of numbers. This looks promising, but hold on. What is going on? We're actually getting like multiple arrays of embeddings, it almost seems. Why are we getting so many? And I actually intentionally let this happen because there's a good chance you might come across this as you're looking to use Inference API, and I want to show you how to get past this. So if we actually look at the output length, actually it's a 3-dimensional array. Let's just take a look. I think it's going to be 1. Okay, let's take a look at the first result. Right, TypeScript doesn't know if it's a number, an array of number, or an array of numbers. Since I'm just trying to prove a point, I could just cast this, but let's do things properly. Let's grab our result as the first element of our output, and then we can check if. Right, so we're just using a type guard, right? At this point, it doesn't know if we're a number, an array of number, or an array of numbers. As soon as we check that it's an array, it at least now narrows it down to those two. Let's run that, and we didn't save it. Okay, the array length is 7. Interesting. Where is 7 coming from? And if you recall, it almost looks like 7 embeddings. And we were expecting, well, 1 embedding, right? You give it a sentence or paragraph or whatever, and it should give you a single embedding with, well, in this case, we would expect 384 dimensions. So why 7? So it's 7 because the way these models work under the hood is they're actually generating embeddings for each token within that sentence. So this input, which I think is using WordPiece tokenizer right now, be good to double check this, is likely producing 7 tokens. And when you run those 7 tokens through this model, it's actually generating an embedding for each of those. And these single sentence embeddings that we are used to is actually kind of like an aggregation operation on these 7 embeddings. Typically, it's this operation called mean pooling. Yeah, if you come over here, you can see they're using this average pooling algorithm, also known as mean pooling, that is actually taking those, in this case, 7 embeddings and using this pooling algorithm to generate a single embedding from those. So what's going on here? Do we actually need to be performing some sort of extra step? Well, yes, another step does need to happen, but I'm going to say it doesn't necessarily need to be done by us. There's some things we can do to get Hugging Face to do this for us. And just to show the kind of the expected outcome, let me show you another model real quick. Let's come back to the leaderboard and let's choose this all mini LM L6 V2 that we were talking about earlier. Notice it's also 384 dimensions. So we'll copy that model, come back here, paste it, we'll save, we'll run, and let's just remove this and we'll just go back to our regular console.log output. And there we go. Pretty much what we expected from the start. There is our single 384 dimension embedding. Perfect. So at this point, maybe this is all you needed. You're like, finally, it took you long enough. Thanks for showing me that. See you later. And if that's you, have fun. It was a pleasure. But I'd like to explain right now real quick why this embedding model produced it quote unquote properly, whereas the last one didn't. And I had to dig into this a little bit actually. And what's happening under the hood here is if we pull this guy back up, our first model that wasn't really working as we expected, you'll notice that we have a couple different, what I'm going to call tags at the top here, right? We have feature extraction, which is the task that they've tagged on this model, right? And this is intentional. We have some other miscellaneous tags on here, but notice compared to our all mini L6 V2, which has this sentence transformers library tagged on there, our E5 small V2 doesn't. And that small detail is actually what changes the functionality, as I've figured out. So under the hood, I'm pretty sure what's happening here is Hugging Face, with their Inference API, they've designed it to look at these tags as little hints and pointers on how to actually execute the inference. And understandably, right, basically what Hugging Face is trying to do is take like all of this large group of various different models that are designed for many different purposes and can be run essentially in many different ways and try to kind of unify that into a single API. And to their credit, that's a somewhat challenging task, right? So I think what's happening here specifically with the sentence transformers is under the hood, when they see the sentence transformers library tag, that indicates that they should be running this model directly through the sentence transformer framework, aka our good old SBERT framework, and use a default configuration that will produce that single embedding as we expected. So under the hood, it's actually automatically performing that mean pooling algorithm for us. Whereas without that, my guess, and I am guessing here, is that we're actually running this model through the Transformers Python library, which is different, more generalized, which will result in a set of outputs that look more like that first set that we got. And then you have to run this average pooling or mean pooling on top of that manually. So if you're like me and you're thinking, well, dang, I would have liked to use this E5 small v2 model. Ideally, I'm not performing that mean pooling myself. Is there any way I can tell Hugging Face to run this model as if there is that sentence transformers tag? And the answer to that, as far as I'm aware today, is no. However, there is a solution. What I've done here is I've essentially forked this model, cloned it, and pushed it up to my own repository with basically the only difference of adding this sentence transformers library tag. And if we go ahead and copy that, paste that into our code and run it, you'll see we're now getting a single one-dimensional array as we would have expected. Awesome. So to me, naturally, the next thing to do here is, well, let's test this out. How can we essentially just get a feeler that this embedding is doing what we expect? So of course, to test an embedding, we basically want to have two embeddings to compare with each other. We can run a similarity algorithm to observe how similar these two sentences are. So let's call this one output 1 and 2, very uncreative names. And assuming these embeddings are normalized, let's go ahead and create a dot product function, just because that's the easiest one to implement and also the quickest to run. So we'll go function dot product. We'll give it a vector A. It's a number array, and B, also a number array. And if you recall, dot product is literally just multiplying each element from one vector with the same element from the other vector. So we could probably use like a reduce here or something, but sometimes I think there's situations like this where the best type of loop is a classic for loop. So we can say let result equal 0. Let's do a good old classic for loop. Oops, let I equal 0. And we'll just add to result the product of A at that index with B at that index. And we'll return a result. That simple. And in production, we might do something like if A.length does not equal B.length, right? These need to be the same length in order for this to work. Then maybe we throw an error. Okay, and then we can do a similarity score equals the dot product of our two outputs. Yes, once again, TypeScript doesn't know what kind of type we're dealing with. Let's do a type guard. So we need to check the first element. Actually, I'm realizing the type guards here are a little bit trickier, just because if you look at the return type here, feature extraction output, it's a number or an array of numbers or an array of array numbers, and that itself is an array. So we need to verify that the elements within the array is essentially not any of these two and only this type. Okay, I'm gonna really quickly create a user-defined type guard here. This is definitely on the TypeScript advanced side. Don't dwell on this. If you're curious, you can check out this code on GitHub to see exactly what's going on. Awesome, there we go. We'll console log our similarity and let's see what we get. Rate limit reached. Please log in or use your API token. Right, so after all this work of us creating our Hugging Face token, I'm just realizing right now that we're not actually loading this token properly. If you remember, I got you to install the .env package, but I forgot to actually use it. Let's go ahead and do that right now. So we're gonna import config from .env, and before we do anything else, we call config, and we can pass in the path to our .env file, which is .env.local. So this was our missing piece. As soon as you call this, it will automatically load in the environment variables from this file into our process.env. Let's go ahead and run that again. And we get quite a strange similarity score. In fact, it's negative. And really, I expected them to have a similarity score of, well, basically 1, right? This is a happy person, this is a happy person, they're the exact same input. So in theory, we should have had like a 100% similarity. What's going on? Well, here it is. I'm not actually doing a dot product. I am summing the two elements together instead of multiplying them. Whoops. Let's correct that. Come back down. Let's give it another go. And 0.99999, that is good enough. Essentially, that's 1, just that can be attributed towards rounding errors. Perfect. Well, this has proven a couple things for us just now. This has proven that we're able to actually truly get embeddings to work using one of the models that we've chosen from the MTEB table. This also proves that this API is producing normalized vectors, because if it wasn't normalized, then our dot product would not work as we expect here. And now I think the true test is going to be comparing two different sentences that are somewhat similar and then again that are quite different. So if we said this is a sad person, what's that mean? I mean, let's just see what happens. Interestingly, it still scores quite high. And I think that's fair, right? Because, I mean, similarity isn't just based on sentiment, right? Oh, happy is 1, sad is 0, or however you might interpret that, right? You have to take the full picture into account. This is a happy person, like the whole context of the sentence, these are actually very similar, right? But if I said, that is a happy person, then I said, the roller coaster is red. Let's go ahead and compare these. We get a lower score. Now, one thing I would keep in mind when it comes to embeddings is don't let the absolute value of this score trip you up too much. I think every model has its own kind of threshold with regard to what you might consider similar. For example, I've noticed with OpenAI, I can feed OpenAI's embedding model two very different, very dissimilar sentences, and it will actually still score quite high on an absolute scale, like say in the 70% range, but it'll never get to like say above 0.8 something, like in the 80% range, unless they were truly similar, right? So again, don't let this 77 confuse you too much. What I'd say is do your own testing on what you expect things to be similar on. Find where that threshold is. Is it 0.85? Is it 0.86? Whatever it is, and use that as your measure to actually determine whether things are similar. And I think every model is going to be different as well. Just for fun, maybe let's go ahead and compare the all mini model. Interestingly, that one is way down at 0.22. Let's try our sad person example. 0.65, change it to a happy person, 1. So interestingly, with the all mini, that one actually varied quite a bit more. So your mileage may vary. Go ahead and test out your content on different models, see how they behave, as each of these models is truly trained on different data sets that may or may not be closer to your content. So I think that just about covers the Hugging Face Inference API approach to generating embeddings. There's definitely a lot more to talk about with regard to the Inference API in general around the other models, but I think that can be explored in another video. So now, for the moment, I'm sure many of you guys have been waiting for, let's actually generate these embeddings locally from Node.js directly on my machine. And with this approach, we can essentially run this completely offline. So what I'm going to do real quick here is I'm actually going to convert this project into a monorepo just so we can keep track of each of these different approaches. Hold tight for 2 seconds. So real quick, all I did here was I took the project that we had before, put it into a subfolder here under apps, and then I just created another root level package.json, which just represents our project root and keeps track of our workspaces that are all going to be under apps for now. And this is great because now I can create another folder here called Embeddings Transformers. And as always, have a simple emoji hello world, which is working as expected. So we're calling this project Transformers because if we head on back to the Hugging Face documentation, we're going to find our way over to the Transformers.js library. And if you've been involved at all whatsoever in the AI ML world from the Python side, you are no doubt familiar with the Transformers framework for Python. And Transformers.js aims to be the, as you'd expect, the JavaScript equivalent to that. Now, there is a lot of work to get feature parity there. Not sure if we ever will, but the fact that this is a thing is quite incredible. So what really is Transformers.js? As they say here, state-of-the-art machine learning on the web, run directly in your browser with no need for a server. Crazy. Now, with that said, we can run this on a server, a Node.js server, as we're about to do right now, if we want to. And the reason why we can do both is because if you come down here, you'll notice that Transformers.js uses what's called the Onyx runtime. What is the Onyx runtime? Onyx runtime aims to be an inference engine that works in many different languages, JavaScript included. And as you can see here, they have bindings for Node.js, for the web, which is accomplished by using WebAssembly under the hood. And they even have Onyx runtime for React Native. So in theory, you can run these models in your mobile React Native application. And back to the web runtime, if you've been following the web GPU stuff that's been coming out recently, Onyx is actually already starting to target web GPU, which is huge. So this is the engine used under the hood. Transformers.js essentially does the job of bundling the most common tasks and use cases into an easy to use API, just like the Transformers library on Python, and we'll use the Onyx runtime under the hood to accomplish that. If we scroll down here, you can see the parity between Python and JavaScript, right? Python Transformers library revolves around this idea of this pipeline, which the JavaScript version mirrors with just the JS equivalent syntax. Here's where you can see which tasks are supported today. Not all tasks are, but thankfully in our case, feature extraction is indeed supported. So let's give it a shot. So we'll come to installation here and we're going to install the Zenova Transformers package. I want to give a quick shout out to Joshua, the guy behind this library. My understanding is that this library was created just earlier this year, 2023, just under 6 months ago by Joshua. And Joshua actually just recently joined Hugging Face, which is awesome. Congrats. Really awesome work on this library, and I am super stoked to see future iterations on this. All right, so we're gonna go ahead and copy this, install that package, and then we'll come on down to the pipeline API. The way this works is you'll first create a pipeline based on the task that you're looking to accomplish. In our case, feature extraction. It'll give you a resulting function that you can now call with different parameters based on the task that you're looking to do. In this case, they're showing you how to do sentiment analysis classifier, and this is how you would run it. And like, hopefully this is inspiring to you guys. Check this out. Automatic speech recognition. We're using the OpenAI's famous Whisper model, which is actually in fact open. And using Transformers.js, we can literally transcribe audio directly in JavaScript, whether it's the browser, Node.js, wherever we want, using this library, which is amazing. As you can see, we can also pass in additional options. So let's go ahead and do this. We'll come back here to the top and we're gonna import pipeline. And we'll go ahead and create a function. I'm gonna call this generate embeddings. And this is going to be the pipeline for feature extraction. And if you're unsure exactly the spelling here, I would just come back to the overview here and you can come down to the supported tasks once again. And there we go, feature extraction, that's the ID for it. Okay, and then for actual usage, we can come back to the left-hand side here and come on down to pipelines. And there's examples for each of the pipelines in here. So if we just search for feature extraction, come on down to here. And we've got a couple different examples. The one I think that's closest to what we're interested in is for calculating embeddings. And if you look at this model actually might look familiar to you, the good old all-mini LMV2. So I'm actually just gonna go ahead and copy this. Note, I actually got this wrong earlier. It should have been an await in front of the pipeline. That's a asynchronous operation. And then we can go ahead and run the embedding generation. I called mine generate embeddings. We'll just have to replace that. And there's a couple parameters here. I'll explain these in a second, but let's go ahead and just run it. Amazing, look at that. So the output format is slightly different. You'll notice it's actually this, what's called a tensor. And this tensor comes from that Onyx runtime under the hood. And it's just essentially a wrapper around that same embedding array that we would have had, right? So we just have a couple additional things like the number of dimensions are shown here. The type, the data format here is actually a float32 array. And then we have the size. So if you're following along, first of all, congrats. You've potentially generated your first embedding locally on your own, but there's a couple things we need to talk about with regard to what's happening under the hood to make this work. So number one, the model. How did we just run that model, right? Theoretically, if we generated these embeddings locally, this model must live on my computer somewhere, right? So are all these models like bundled into this package? No, and thankfully no, because that would be insane. What Transformers.js is doing under the hood is they're actually fetching this model from Hugging Face on the fly. And actually, I believe caching them. Take a quick look here. Yeah, you see under the Zenova Transformers node module, they're creating this .cache folder, which is caching our all mini LM model. So this is important to note, right? Because when it comes to deploying this application, you need to keep in mind how you're distributing these models, right? You need to ask yourself, am I okay with Transformers.js fetching this model on the fly from Hugging Face at runtime? Or would I prefer to maybe prefetch that model and distribute that with my application? Like say you're creating a Docker image for your app, you may or may not consider actually just embedding that model directly into your Docker image. Now, your decision on that may depend greatly on how big that model really is. Thankfully, all mini LM is quite tiny relatively, so it's in the matter of tens of megs versus hundreds or gigabytes. So potentially this could be something you can embed right into a Docker image. How do you do that? Well, if you look into their documentation, they have this section on custom usage that explains that you can actually download these models manually. So you would literally go to the Hugging Face model and you would come in here and you would download these files locally. And the files you have here are actually important. So we'll talk about that in a second. But the idea is you would download the model yourself, set this special configuration to point to that local model, optionally disable it from fetching remote models from Hugging Face at all, and go from there. So that's the first thing to note. Second thing to note is you might notice that this model actually lives under Zenova's Hugging Face organization. And in this particular case, the reason for that is because in order to run your models through Transformers.js today, they need to exist in a special format that can run in the Onyx runtime. And by default, that's probably not the case for most models, right? If we come back to sentence transformers, for example, check out the files, you can see that this is actually a PyTorch model and it's around 90 megabytes. Actually, it looks like they have a couple different ones. They also have TensorFlow down here. PyTorch is the most common one you see today, which naturally must run within Python. If we look at the E5 small, same thing. It's a PyTorch model. This guy's 134 megs, etc. So let's go ahead and take a look at the Zenova one. Here it is. If we look at the files, okay, we don't have any PyTorch model. We actually have this Onyx folder, which contains our model built for the Onyx runtime. And by default, this model is 90 megs unless you quantize it, which I'll talk about in a second. And if you use the quantized model, you can actually get down to 23 megs, which is insanely small. So hopefully it's clear that this is a very important detail. You can't just take any model like we've been doing and pasting them in here. Let me just do it quick just to prove my point. We get an error that says, cannot locate file Onyx model quantized, right? So it's looking for that special Onyx folder along with the model in the Onyx format. So at least today, in order for your models to run, they will need to exist in that format. And this is kind of the compromise, right? In order to get it to run this way. This might not always be the case, but it is today. Now, if you're thinking to yourself, well, dang, like that must severely limit me just to models that someone like Zenova has created. And thankfully, you have a bit more control than that. If you come back to their documentation, you can see there's a section here on how to convert your models to Onyx format. So it's actually relatively straightforward. Transformers.js comes with a Python convert script you can check out, which can convert a PyTorch, TensorFlow, or JAX model to Onyx. And under the hood, it's using Hugging Face's Optimum tool to do that. So just like I did earlier, where I more or less forked one of these repos just so I could add my own tags, you could do something similar with the exception of doing a little bit more work. You just need to run the model through this conversion script, push that up to a model, and you should be good to go. Also worth noting real quick, these models are actually just Git under the hood, if that wasn't already obvious. We have branches, we have commit history. It literally is just Git under the hood, with the exception of it uses Git's large file system extension, which allows you to store like very large, massive files within Git, which was previously taboo, bad practice, something you really never want to do. But the LFS solves that problem and makes it actually functional within Git. So you'll need that Git extension if you don't already. There is instructions on how to do that if you need to. Okay, the last thing here, you might notice this quantize flag here, or down here we have our model and our quantized model. What does that mean, quantized? Think of quantizing as kind of compressing your model. Compressing is maybe not the right word here. It's basically reducing the precision of your model. So if you're familiar with how information is stored on disk, most models will use a floating point 32, which means it's using 32 bits or 4 bytes to store that on disk. And with quantization, you can reduce that to most commonly down to 8 bits, which is 1 byte instead. So you can reduce the size by up to 4 times by using quantization. And if you're wondering, well, we're losing precision, so that must be worse, right? The answer is yes, it will be. But you might be surprised sometimes how well the quantized models can still perform. I wouldn't say by any means that reducing the file size by 4 times means it's 4 times worse by any means. I mean, you still have that model trained on the same data. It's just less precise when it goes through its inference. So test out both models, use whichever one works best for your application. You might find that the quantized models are really great for embedded systems or when you're running them directly in the browser. At the end of the day, you'll need to load these into the browser somehow, right? So a 20 meg file versus a 100 meg file can make a big difference. We're talking about a lot of things right now, but this is because we are doing a lot of this work more manually, right? Okay, the last thing we need to talk about here is these parameters. We have a pooling and a normalization parameter. Hopefully you can make a pretty educated guess by now what these are doing. You hopefully recall me talking about mean pooling earlier, where we need to take the separate embeddings generated for each token and aggregate them into a single embedding. And most commonly we do that through a process called mean pooling. So Transformers.js actually has that algorithm built right in. And so all we need to do is tell it to use mean as the pooling method, and it will do that for us. And second, we're actually asking it to normalize it as well, which means they'll all end up as unit vectors, and we can use something like dot product to compare them. So without further ado, let's mirror our setup that we did in the other project. If you recall, these outputs are actually tensors now, so we need to compare the dot data. We change this to that is a happy person, and we should expect a similarity of basically 1. Let's try it. Oh, we forgot to change this model back. Boom. And if we go ahead and do that test, this is a sad person. What did that end up as? We're using the all mini model. I think that was around like 60 or 70. 65. I'm pretty sure that's nearly exactly what we had before. Maybe a minor precision difference. So let's just note real quick what would happen if we didn't normalize these. 15, right? So we wouldn't be able to accurately use dot product here without that normalization. And then without that mean pooling, let me just do a quick console log of the first one here. You can see our size is very different. And actually what's happening here is this is like the raw underlying data on disk. So it's still 384 dimensions, but that's times 7. And if you recall before, that is a happy person, that was actually also tokenized into 7 tokens. And just like in that other demo, when we didn't have mean pooling happening, we had something similar to this, right? And then with that enabled, we are getting our proper 384 single dimension array. So hopefully that's clear what's going on there, why those are necessary. Okay, so we have a proof of concept of using transformers from Node.js. Now let's finally do a quick demo on how we can do this right in the browser. And spoiler, it's not much different than what we've already done here. Now, typically in these situations, I would probably spin up a React project. I would probably use something like Next.js to scaffold out a nice front end. But I think what I'd like to do today is actually just go pure vanilla HTML and JavaScript, just because I want to show you literally how simple it is to run this in the browser these days. Of course, what I'm about to show you will absolutely translate. If you're in React, you might be using Next.js or Vite, or you might be coming from the Vue side, or even maybe the Angular side, or really anything else. So hold on for 2 seconds as I quickly scaffold out our third app. All right, so what I've done here is, just like before, I've added a new project in our monorepo, this time called Embeddings Browser. And this project literally only contains these 3 files: our HTML itself, our main JavaScript file, and some CSS. And again, what I'm about to show you will absolutely translate to any other front-end framework, but my goal here is to show you just how easy it is to do in literally a vanilla setup. Okay, so real quick, I've already scaffolded out this HTML just so we're not wasting time with layouts. I'll show you what it looks like. This is it here. So I was trying to keep things literally as simple as possible. I got 2 inputs, and a button here called calculate similarity. And the idea is similar to what we were doing earlier. We will generate embeddings on two separate inputs, then use dot product to calculate the similarity between them. Styles.css is just so that it doesn't look ugly. Again, not putting a ton of time into this, but come on, it's got to look presentable, right? And then finally, we have our main.js, which as always, we're going to test out with a console log. Now, worth pointing out real quick, the way I'm loading this script is important. We're going to take advantage of a new browser feature called ES modules, which allows you to essentially do modern JavaScript. So things like imports, top level await, all that kind of stuff. And no, I'm not using any kind of bundler right now, like Webpack or whatever. This is truly vanilla JavaScript right now. Another thing worth noting with this script is I am using the defer attribute, which basically says wait until the entire DOM has loaded before running this script. And that's important because we're basically going to get access to these different inputs within the DOM, and that will only work if the DOM has already loaded. So in the past, you might have used something like the DOM content loaded event, where you say document.add event listener for this DOM content loaded, and you would only run your script after that. Now we can just use defer instead. Okay, so moving into our main.js, let's test out our wave emoji. Oh, and by the way I'm loading this HTML file in my browser is using an extension for VS Code called LiveServer. LiveServer is a super handy tool just to quickly spin up a local web server to serve your HTML. Other front-end frameworks like Next.js have this built right in when you run npm run dev. But if you're just looking to spin up a quick live server like what we're doing right now, this live server extension is super handy. So would recommend. So I just have to right click and say open with live server. That will spin it up on the fly, and I'll essentially get access to my live server right here. Okay, so we'll refresh the page, check out our console. There's our emoji, perfect. We have a starting point. Let's get going. So making our way back to the Transformers.js documentation, we're going to come back to installation. And you may have noticed before, in addition to the npm install method, we actually can use this modern ES module import. And modern imports import directly from URLs. Fun fact, this is exactly how Dino works as well. Dino is a backend alternative to Node.js, but what Dino tries to do is it tries to follow the browser spec as closely as possible. So the idea is if you can run this in the browser, hopefully it would also work in Dino. Now, we're not using Dino at all today, but there's a fun fact for the day. Okay, so I'm going to go ahead and copy this import. I'm not copying the rest of the script because I've already done this, right? In my HTML with type module. Did I mention that? Maybe I didn't mention that. In addition to everything else I said, you need to add the type module attribute to your script in order for browsers to treat this script as a modern ES module script. So I've already done that. I'm just going to copy this import, and we're not doing it in line like them. We're doing it in a separate file. Going to paste that here. So just like before, this will import the pipeline function. And then before I go ahead and copy over all the same functions that we did in the Transformers project, we need to do one more thing real quick, and that is create some references to our HTML elements. So we're going to need access to each input. So input 1 and 2, we're going to need access to this button. And then I actually have another, it's invisible right now, but another div down here that will contain our output. So we'll need access to all 4 of those things. Those exist right here. I have an ID for each one. So input 1 to our generate button and our output div. Let's go ahead and do that now. Okay, there we go. And again, we don't need to worry about first checking if the document has loaded because we used the defer. So we can guarantee that the document has loaded. We'll get access to each of these. Okay, next I'm going to go ahead and just copy over the same functions from the Transformers project. The first thing I'm doing is creating this generate embeddings pipeline, just like before, and we're using ES modules, so top level await is fine. Unfortunately, we no longer have TypeScript, so we'll need to get rid of our types. And I'm just copying over the dot product function again for now. Okay, and this is where we'll have just a slight difference where instead of going ahead and generating those embeddings right away, I only want to generate them when someone clicks the generate button. Let's go ahead and add that click handler. Okay, we have our handler. We can go ahead and copy our other generate logic into that. We're using await, so we'll just need to convert this to an async function. And then instead of hard coding these values, we'll need to just grab these from our inputs that we created earlier. And then finally, instead of console logging, we're just going to go ahead and take that similarity and we're going to insert that into our output div. Perfect, let's give it a shot. Oh, you know what? I forgot to do one thing. This button I disabled by default. You see here, button is disabled. The reason why I did that is because this async logic to construct our embeddings pipeline actually takes a little bit of time. And as I'll show you right now, it actually will take the longest the very first time because it has to load that Hugging Face model from Hugging Face. But then what Transformers.js actually does for us here is they will cache that model in the browser so that every subsequent reload, that model is actually already available, which is amazing. Much needed for any machine learning related application because these models can be quite huge, right? Even the all mini LM v2, as we talked about earlier, is quite small relative to the other ones, especially the quantized one is 20 megs. But even from a browser context, 20 megs is still quite a bit, right? Those who have worked in a web environment know that, every kilobyte adds up, right? And depending on the website that you're building, you really want things to load as quickly as possible. So anyways, that caching is important. So because of that, what I'm going to do is after our pipeline has loaded, now is the time I'm going to go ahead and re-enable our button. Of course, in a production application, you would most likely have some sort of loading indicator. That would be a much better user experience, but this is just a demo after all. Okay, first thing to note here is we're actually getting some 404s in our browser. What is going on? And if you take a closer look at these, you'll notice that the Transformer.js library is actually trying to load the model from our local host. You can see here, right? It's looking for a model on the /models, Zenova, blah, 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 the model's path. And what's actually happening here is it's basically first checking to see if it's already cached. That's what these calls are all about. And if it's not, then it goes ahead and, as you see here, these 404s, it didn't exist locally. So what it is it went ahead and fetched them from Hugging Face instead. And I'm really zoomed in here, so apologies that everything's kind of getting cut off. It's a compromise when trying to make everything readable here. And you don't really need to know this, but of course, I need to show you this anyway. If you're wondering where it's actually cached, come on over to Application in your DevTools. And then over here where you might have gone to, say, local storage in the past or cookies, there's another one here for cache storage. Expand that out and you can see that the Transformers.js has created a cache entry here, which in this case has, well, you can't see them here. Let me just expand this out. There we go. So it's cached just the config file, the tokenizer file, and the model itself. And that means now if I refresh again, look how quickly that loaded. The button became enabled. That means that it was actually able to load that model now that quickly, which is amazing. If I go back in here and delete this entry, notice how long it will take this time. A little bit longer. All right, now for the moment of truth, let's see what our similarity is. We have the classic, that is a happy person on both. So once again, with the mini model, we should be expecting a score of 1, or as we found out with the precision difference, just over 1. Awesome. And then just like last time, say we said a sad person, we know now that this should be around 0.65. Let's give it a shot. Boom, 0.65. And look how fast that is. Every time I click calculate, remember, I am literally generating an embedding for actually 2 pieces of text and performing the dot product. So that is quite speedy. Okay, so that's just about it, guys. If you're still here, thanks for following along to the end. I know this was a longer one. Once again, I will be pushing all this code to GitHub so you can reference this as well, and feel free to clone this repo and try writing it yourself. Now, there is one last thing I need to finish with, because at the beginning of this video, I promised that I would be talking about the future of embeddings and what's coming up on the horizon. So what is next? So at the beginning of this video, I briefly touched on the multimodal image and text embedding models, specifically this CLIP model, which stands for Contrastive Language Image Pre-training. And this is actually from OpenAI. Again, this one is open source. And as we talked about earlier, what these models allow us to do is generate embeddings from 2 or more different media types. So in this case, images or text, but the resulting embedding is produced in the same joint vector space. And this last piece here, that is, in my opinion, the incredible piece, right? If it wasn't clear up until now, every single embedding model will produce embeddings in different vector spaces, right? I can't compare an embedding from one model with an embedding from the other model. It would be meaningless. The meaning of those vectors would just be completely different for each model. So the ability to generate 2 different things into the same vector space, meaning performing a similarity between those 2 embeddings is actually meaningful, is huge. It's, in my opinion, this is massive between 2 different media types. And I don't have time right now to go deep into how they're actually able to accomplish this, but what I will do is point you to their paper, Learning Transferable Visual Models from Natural Language Supervision. Check out their paper here. Now, their paper actually focuses more on the idea that previous vision image-based models were trained on a fixed set of predetermined object categories, right? So like my example earlier, training a model with pictures of a hamburger, but then I need to actually add that label hamburger to train it what that is, right? They're trying to come up with an approach to be able to label things without actually training the model with each label corresponding to each image. As I say here, it restricts their generality and usability since each label has to be basically predetermined, right? So what they're actually trying to do is come up with a generic way of image captioning without like this manual fixed set of labels. And as we talked about before, we call this zero shot. So if you're like me and wondering how is this actually possible, what they're doing here is, as opposed to the traditional way, which is training an image feature extractor with a linear classifier to predict some label, they're instead jointly training an image encoder and the text encoder, and they're maximizing the cosine similarity of the image and text embeddings that were produced while minimizing the cosine similarity of the incorrect pairings. And so they're basically using that to train the model to produce embeddings in the multimodal space. And since this paper, there's been more work on this. There's another one called Embed Everything, a method for efficiently co-embedding multimodal spaces. This is in October 2021. And for these guys, the message they're trying to get across is with AI blowing up these days and more companies using AI in their businesses, we're going to need a good way to, as I say here, interpret, operate on, and produce data in a multimodal space. This would include audio, images, text, anything else. And as they mention here, lots of success in the unimodal space, but when it comes to multimodal, techniques are somewhat underdeveloped, right? It can be potentially pretty expensive and not straightforward to train these multimodal models. And they're proposing a new approach to help generate these co-embedding multimodal spaces that is more cost effective, utilizes existing pre-trained models, etc. So if this is something you're interested in specifically, feel free to read this paper as well. Really cool stuff. But this is just something I wanted to add in here because I think this captures quite well what's coming up in the future, right? I believe there's going to be a big focus on these multimodal spaces and the ability to generate embeddings that work in all of these spaces, right? It's already very useful to generate embeddings for just text and being able to determine the similarity between them, but just think of the possibilities once we are able to actually compare audio with an image with text and they're all in the same vector space. The things that computers will now be able to understand, I think will open a lot of doors. All right, you made it to the end. Congratulations. Give yourself a pat on the back. This was a long one. I hope you learned something new today on embeddings. I'm really excited to see the kinds of things you guys will build with embeddings, maybe now with some of these open source models. Thanks so much for watching, and I'll catch you down the next rabbit hole.